Morning again. Welcome to our interesting section about impacts and modeling. This section will have 4 presentations, 50 minutes each one. I will show you a piece of paper when it's finishing, 2 minutes before the end. And we will have a altogether discussion at the end of the section. 15 minutes also to the questions, comments, and what we need to do. And we will start with Michael Diamond from Florida State University, our first presenter in this morning.
So much for having me. My name is Michael Diamond from Florida State University in the United States. I'm going to be talking today about an idea that my group is developing. I'll use developing as in a very active sense there. I'd love any feedbacks. This is kind of just a first pass at this. So our motivating question is, would solar radiation modification affect shifts in climate zones? And in a slide or two, I'll get into a little bit what I mean there. I do want to make sure that I'm clear that the work I'm presenting is largely done by my very talented undergraduate student, Jay Brunelli, who, unfortunately for me, is very keen to get out of Florida. So she will be on the market for any potential advisors out there if you're scoping right now. Keep an eye out. So climate zones. There's this idea that kind of comes out of work from Vladimir Koppen in the late 1800s, has been refined a bunch since, but how do we take all of this chaotic information about temperature and precipitation and diurnal ranges and what vegetation lives where, et cetera? Is there any way that we can categorize that in a way that can be more manageable and useful, right? So you want to make it finely detailed enough that it is usable and something that gives you good information, but also something that you could actually more easily digest than just some world map where every little place is its own special snowflake. So Koppen came up with a classification based on different statistics of temperature and precipitation. And we're going to be using a modified version of that. So to make this maybe a little bit more concrete, what we're talking about, so we're going to divide the world into some big classes, going from tropical regions, arid regions, subtropical regions, kind of like where we are now, temperate regions, and polar or subpolar regions. So imagine in some present day, I kind of did a 50% transparency over all of these. We have some distribution of these zones in the present day, right? One of the big concerns we have for climate change is that these zones are going to change. So what we would expect under a relatively worst, I don't want to say worst case scenario because I've seen how the world's evolved over the last 5 years, over a relatively high emissions case scenario, right? We would expect these zones to shift. Something like we're going to get a huge reduction in polar areas. Those are going to become more like temperate or subtropical areas. Some subtropical areas are going to become more like tropical areas or arid areas. We're going to get an increase in precipitation, but also a lot more evaporation. Maybe we even get some tropical areas becoming arid areas. And when we're thinking about the burdens of adaptation from climate change, right, this is what really we're thinking about on a local scale. We had some climate conditions that we were used to, that our ecosystems were used to, that our societies were built around. And that is now changing in flux. So let's say we get on a much better pathway. We cut CO2 emissions by quite a bit compared to a very high GHG scenario. We'd get the same thing, right, but a lot smaller, maybe a lot more manageable. So the big question motivating our work here is now let's say we're on the high emissions trajectory from before, and we apply solar radiation modification. And we have, from the modeling and from our understanding of atmospheric physics, a very strong idea that we can put the global mean surface temperature back to about the point where we found it, or where we might want to get it. But that's not the whole story, right? So maybe if we did that, it would look kind of like the world in which we just cut emissions in the first place. But maybe it would look really different, because we're doing something really different to the system, right? Maybe instead of putting the world kind of back the way we found it, we get the same global mean surface temperature, but now we're getting these big regional shifts in temperature. So some areas that were temperate are subtropical, some areas that were subtropical are temperate. There's going to be a big reduction in precipitation if we were to fully offset a CO2-driven warming with aerosol-based cooling. So maybe we get a huge expansion of arid zones. So those are kind of the hypothesis. What would a world under SRM look like in terms of these shifting climate zones? And is this maybe a useful way of quantifying these concerns that we have about non-uniform shifts? And just a little bit more about that for anyone who is less familiar. Over here, I have just one climate model, but any climate model would be qualitatively similar. In the red is the temperature pathway that you would get under a very high greenhouse gas emission scenario. This is actually SSP 5.8.5. In the blue is the temperature change you would get, global mean surface temperature change under a lower emission scenario. And in the yellow is what if you applied stratospheric aerosol injection on top of that high greenhouse gas emission scenario to keep the global surface temperature the change, right? And in model world, again, we can do this really, really well. We can hit that temperature target. We don't hit the same precipitation. We know really well from fundamental physics, if you keep that CO2 in the atmosphere and don't have an increase in surface temperature, that's going to lead to a large decrease in global mean precipitation. Not really relevant for the land-based climate zones I'm talking about, but also does nothing for ocean acidification. So the approach we're taking here is we're using the G6 sulfur suite of simulations. I'm going to show results now from CSM WACM, but Jay is currently working on the other 5 models in that series, where this was an equatorial sulfur injection to go from the red line here down to the yellow line there. We're going to use the Köppen-Schwarthe climate classification system applied to a global climate model. This is actually not the first time this has been used. This paper from Ulrike Lohmann in 1994 actually already proposed using Köppen-like classification systems for climate model evaluation diagnostics. Jay was very fond of pointing out this looks like an old Pokemon game. It probably came out at about the same time. So we'll use a slightly updated version of that. And to make this concrete, we're going to have these 2 hypotheses that we're trying to test. One is that stratospheric aerosol injection will reduce shifts in climate zones pretty effectively, similar to as if we had just mitigated with greenhouse gases. So basically, it will reduce these shifts in climate zones broadly as a function of global mean surface temperature. And I'll say that when I say SAA quote-unquote works, that's what I'm going to mean. In the second hypothesis, this is SAI quote-unquote does not work. We're still resulting in a bunch of shifts in climate zones, maybe even rivaling the magnitude of shifts in SSP 5.8.5 or that high warming scenario. But now we're doing it non-systematically in temperature, but systematically towards drier climate zones. So in terms of what it would mean to adapt locally, this might be as much of a burden as maintaining in a high CO2 world if you think this hypothesis is true. And this is where I'm going to make you guys do some work. So before I get to the results and a little bit more about these climate zones, I'm going to see, so our hypothesis 1, SAI basically works to reduce shifts in climate zones. Hypothesis 2, SAI causes so much climate weirdness that it does not work to reduce shifts in climate zones. Let's get some hands. So who thinks that we are going to find, at least in CSM WACM world, that hypothesis 1 is true, that SRM effectively reduces the adaptation burden from these climate zone shifts? Okay, hands down. How many people think it's going to be hypothesis 2? Say it does not work. Okay. How many people didn't vote? there's a big missing extension here. Okay, so we have maybe a little bit higher for hypothesis 1, but it's pretty split, which makes me feel that we've come up with a good hypothesis if it's not obvious beforehand which one is going to be true. Okay, so this is what we're going to be looking at. And do please, for the love of all that is good in the world, don't try to like find your city and match it exactly. Again, this is pretty crude, but we're going to be looking kind of qualitatively at these types of maps of where these climate zones exist, where these kind of reddish colors over here, where we have arid regions, blue is tropical, yellow is subtropical, the lightish blue, I think they're supposed to be green things, are temperature, and the pink is subpolar to polar in that kind of dark purple. So what do I mean by these classes? And we can be quantitative about it. So our class arid, which I'm actually going to go out of order a little bit with B first. This is our only one defined, at least the class is defined wholly on hydrology. And we're going to classify anywhere in the world as arid where potential evapotranspiration, so how much water can you evaporate, that exceeds how much water you actually get from precipitation, right? So it's dry, is basically what we're saying. It could be dry and hot, like the Sahara. It could be dry and cold, like Mongolia. And it can be kind of dry, like the Great Plains, or the Sahel, or down here in the Kalahari, versus like really dry in the Sahara Desert. In the tropical, we're going to distinguish between rainforests and savanna, where we're defining tropical as every single month has a mean temperature warmer than 18 degrees Celsius. And this at least is doing a somewhat reasonable job, right? We have our rainforests in the Congo and the Amazon. We have some savanna over there. We could, debate boundaries. Our subtropical, we have Mediterranean regions, like here in Cape Town, like the natural Mediterranean, or subtropical humid, like where I live in Tallahassee, which has no dry season. And these are all just going to be based on how many months are warmer than 10 degrees Celsius. So subtropical has more than 8, but is colder than tropical. Temperate has more than 4, but is colder than subtropical, et cetera, et cetera. It's nicer to live in Berlin than Quebec for at least temperature-related reasons in the winter. And then subpolar, think like Siberia, southern Alaska, tundra, think like very far north Arctic, and then ice caps are when it's never above 0 degrees Celsius. So, okay, have this kind of basic picture in your mind. When we look into the future, and this is right now the low greenhouse gas perspective, I'm also adding a couple boxes over here. These kind of new dark boxes are areas that are considered novel climate zones. These are hotter than the hottest single month in the past. That's a kind of working definition right now. Very interested in hearing if people have better definitions there. Okay, so this is what it looks like under low greenhouse gas or moderate greenhouse gas forcing. This is what it looks like under SSP 585, high greenhouse gas forcing, right? You have the Congo and the Amazon being hotter than ever experienced before, even some novel arid regions. So when we apply SAI on top of this, the question is, what are we going to get? We get a map that looks like this, which I'm going to just flip back and forth. If you're eagle-eyed, you can probably see some decent differences between SSP 245 and G6 sulfur, but they actually look quite similar overall. And we can be a little bit more quantitative with this. So these over here are called Sankey diagrams. Okay, and I am wrapping up. Yes. So basically, this is where you started. This is where you're going. So a lot of the areas that started tropical under SSP 585 go into this kind of novel tropics bin. Almost everywhere that started as subpolar under SSP 585 winds up becoming temperate. A bunch of temperate areas become subtropical, et cetera. When we look at this in terms of the G6 sulfur climate zone transitions, we get qualitatively similar but quantitatively smaller shifts into all of these. So what we would expect from effectively reducing the temperature velocity. And when we compare this with SSP2 4.5, If you're really eagle-eyed here, you could see, right, in SSP245, arid regions go down a little bit. In G6 sulfur, they go up a little bit. But overall, it actually looks quite similar. So our conclusion here is that at least in the context of CSM2 Wacom world, and if we believe that these climate zone transitions are a useful measure of the adaptation burden, hypothesis 1 is our clear winner. SAI works to reduce the adaptation burden from shifting climate zones, at least in this context. Thank you so much.
Thank you. Now we are moving for our next speaker. Let me see here. Your presentation. Okay. Please introduce yourself.
Okay. Hi everyone. Hello. Okay. Hi everyone. I'm Mou Leong from Malaysia. So how many of you have been to Malaysia before? Do you know where's Malaysia? Oh, only one, two. Yeah, maybe those from side. Yeah. So Malaysia is like located between Thailand and Singapore. So okay. So actually I'm mainly working on like how SRM could impact the tropical hydrological cycle, mainly in the real basin of Malaysia. But this idea, I mean like heat wave, actually this idea was initiated from our South Asia regional workshop that we organized last year in Singapore. And okay, so actually like in recent year, I mean, especially in these past 2 or 3 years, we started to, I mean, like, aware that actually heat wave is like getting worse in our regions. Like you can see in many cities of South Asia, so the temperatures had hit, I feel like 40 plus degree. Okay, and for your information, actually, like people in Malaysia, at least I can speak on behalf of my own country. So we are well adapted. I mean, I mean with the heat wave, because in Malaysia, in every house we have like aircon. So even in our car, okay, we have air condition. But still in Southeast Asia, in many rural areas, okay, in many rural areas, I mean, maybe they don't have aircon to adapt with this heat wave. And we know that actually Southeast Asia, we also have like quite high populations in some big cities like Bangkok, Manila, and Kuala Lumpur. And last year, so in 2023, so we have like a record-breaking heat wave that hit the mainland Southeast Asia. So this is like, okay, like maybe 5 or 10 years back. So normally I will listen or receive the news about heat wave in European country, right? And that this caused like a loss of human life, like in very high numbers. But in recent year, like for example in 2024 in Thailand, so 36 people were killed because of this heat wave, and more than like 10 million children were affected. And similarly, so recent year, I mean, at least I, myself, and the public of Malaysia, we have received alert or warning from our governments where, okay, heat wave is happening now, so you need to like reduce the outdoor activity, so drink more waters, okay. And so in Malaysia, normally, for our meteorological department, we normally define heat wave as 3 continuous days that more than 37 degrees Celsius. Okay, so they will come out with this alert. And sadly, last year, we have like 2 citizens were killed because of this heat wave, because they got heat stroke, and then when they admitted to hospital, so lastly, they was like passed away because of this heat wave. So like that's why this topic become like, we think that we should study this, like how SRM could actually impact heat wave in South Asia. And we noticed that actually previously there are some heat wave related study in South Asia, but mainly global scale. I mean global scale assessment, or maybe these studies are limited to single model or scenario simulation. So that's why for our study we are going to use the geomet 6. So to study how to analyze how the SRM could affect the temperature extreme and also heat wave in South Asia. And we further divided the Southeast Asia into 20 sub-regions, okay, based on the land area. So this, sub-areas division actually we adopted from the Codex Southeast Asia framework. Why? Like, I give you one a very simple example. So even though we are in tropical region, like for example in Peninsular Malaysia, so we divide into the two parts. So because like the rainfall distributions in the east coast of the Peninsular Malaysia is actually different, slightly different with the western part of the Peninsular Malaysia. Okay, like for example, for east coast part, so normally they are more affected by the northeast monsoon, where the peak precipitations normally happens in December, November or December. Okay, and while in the west part, like for example, in the city that I'm staying right now, Penang, so the peak precipitation is normally happens in inter-monsoon season. Okay, because this area is actually protected by the Titiwangsa Mountains, okay, and also Indonesian mainland. So our peak rainfall normally happens in October. That's why, and then that's why under this Codex Southeast Asia framework, they have like consulted the climate scientists from different part of the Southeast Asia and come up with these sub-regions. And we have like adopted like 4 geomics models for this study, and then and then we try to use the Era 5 data as the observations to downscales and also bias correct the data. Okay. And for sure, this is just we use the bilinear interpolations to recreate the geomics models, and then we apply some bias corrections before we calculate the heat wave. And then we have adopted like 4 main indices. I mean the temperature indices, the annual maximum daily maximum temperature, like the hottest day, and the hottest night, TNX. And also the heat wave number, like total number of heat wave event within a year, and then the heat wave frequency, like a number of heat wave days, okay? And then the longest durations, and also the peak, the heat wave amplitude. So we try to understand how SRM could, affect these phenomena. And then in the early stage, actually we face some like difficulty or challenges in defining heat wave in this region, because just now I've mentioned that like Malaysia, they use like 37 Celsius to 3 days to define as one heat wave event. And then like different countries, they have their own definition. So lastly, we use the 90th percentile of daily maximum temperatures during the baseline period for defining a heat wave. Okay, so we use this. We refer to 2 or 3 articles. Okay, this is the performance evaluations, like before we further calculate or project the heat wave for the Southeast Asia. So we try to use RSE to see the differences between the original and also the corrected corrected models. And then for the original one, the RSE is around like 1 to 5 to 2 degrees Celsius, and then after the bias correction, it can reduce down to like 0.4 to 0.8. Okay, so we reduce around 1 to 1.5 Celsius. Okay, this is just some findings from our study. So this is the temporal variability of the hottest day. Okay, the hottest day in Southeast Asia. So there are 2 main findings that we have found from our result. So like, for example, in R18 to R20 region, which is the continental mainland of South Asia, actually, the hottest day is reduced by an addition 0.5 to 1 Celsius as compared to G6 solar. So from here you can see, okay, the red color represent the SSP 585, and then the blue color represent the SSP 245, and then actually the G6 sulfur have reduced the hottest day temperatures by, like at least lower like 0.5 to 1 Celsius in this mainland South Asia region. But for the region like East Malaysia, like R3 and R4, which is near to the maritime, near to the ocean area. So actually the SRM, how to say, like failed to align with the SS245 for these two particular regions. And then, like, yeah, as compared to the hottest day, G6 solar and G6 sulfur actually perform better, in modulating the temperature increases from the SSP 585 to 245, okay, as compared to the hottest day. So this is the historical heat wave distributions of South Asia that we have simulated from the model. So this one is the amplitude. We can see that actually the heat wave amplitude is higher in the mainland South Asia, like in the northern Thailand, okay, and so on. And then this is the duration. So heat wave durations is like between like 5 to 10 days. Okay, based on our historical record, and then also the heat wave frequency. Okay, like how many days, how many heat wave days. So and also the event. So around like 3 to 5 events. Okay, so like 1 year we normally receive this 3 to 5 times. And then this is the simulation, the future simulation under 4 different periods. We have divided into like a near, mid, and also end of the century. So you can see from this figure that actually the heat wave amplitude, in terms of the Celsius, will increase dramatically, at least 5 to 6 Celsius as compared to the baseline period. Okay, and then both like SRM can modulate these changes to SSP245. Okay. And then like this one is the frequency, how many heat wave days. So similar to as previous findings, but from here we can see actually the maritime regions, like country that's surrounded by the oceans, like the Malaysians, Indonesia's, actually they respond more rapidly to the warming. So the changes is more significant as compared to the inland South Asia. And also this is the changes of the heat wave day. Okay, so the effect is like less in the like early of, in the near 21st century, and then the situation become worse after like 2060 to the end of the 2100. Okay, and also yeah, so like especially like for the maritime region like the Malaysia, you can see actually the SRM can help out to modulate the heat wave increases of the heat wave durations align with the SSP245 scenario. And then this is the heat wave numbers. Like just now I said, like historical period, normally we have like 3 to 5 times heat wave events, right? So from here you can see, okay, actually the heat wave number increased in the mid of the 21st century under the SSP 585, but the number decreased towards the end of the 21st century. So yeah, this is quite interesting finding. And then the reason why is that because the heat wave durations is longer because heat wave duration is longer now, so that's why the number have decreased. Like for example, previously maybe we have like 3 to 5 days heat wave numbers. Maybe each event is just like 3 to 5 days, but in this period, maybe the heat wave duration is longer, even though the number is lower, but the number is longer. So yeah, this is just the density of the heat wave based on the distribution of the grid. Okay, so yeah, under the SSP 585, so for sure the temperature is projected to increase 4 to 6 Celsius, and then the SRM is more effective for the warmest night as compared to the warmest day. Okay. And then like these are some statistics about like the heat wave duration maybe will increase up to 140 to 180 days, and then the SRM SSP 245 will limit these increases to 60 to 80 days. And then also the maritime region are more sensitive to heat wave. And then like for sure in the futures we plan to expand this study by incorporating some population information and also the city, and also try to study how this could affect the agricultural productivity in our regions. Okay, that's all. Thanks.
Thank you. Now we are moving for our next speaker. Just 1 second that I will open the presentation. Okay. Our next speaker is Juan Velasco. He works in Mexico, but he is Colombian. Just 1 second.
Good afternoon. I'm very happy to be here to show these results on our project. This is a collaboration with other researchers from the University of Cape Town. So this project is the aim to evaluate impacts of SRM on biodiversity, but what is the spatial biodiversity gradients? So this is a question about we are biologists or ecologists, have for many years to explain why the distribution of the diversity in the planet. So why are so many species in the tropics? The species are concentrated in the tropics and decrease to the poles. So this is a question for many years. The first one person to know this pattern and propose some mechanisms to explain that is von Humboldt, but probably he stole the idea from Latin American scholar, but this is a problem to resolve another day. So many factors are being proposed to explain that latitudinal diversity gradient. So, but you can classify in historical factors from the past and ecological factors related with climatic factors, temperature and precipitation, and seasonality. So you can use climatic factors to explain this gradient. So you can evaluate the distribution of the diversity in different taxa, amphibians, reptiles, mammals, birds. You can see different patterns, different concentration of species. More dark colors, dark blue colors means more species. For example, you can see mammals and birds have more species in the Andeans region, reptiles in the center of the Amazonas, and amphibians in the Andean or in the southeast Brazil, Mata Atlantica. So we can use that different variables related with that hypothesis, basically water energy balance, temperature and precipitation, and seasonality to explain that diversity and predict the spatial pattern or species richness. So this part is very important because you need to calibrate this model very well to generate accurate future projection of the species richness. So we can find the Annual precipitation is very important for amphibians, and temperature seasonality, and annual precipitation for reptiles. These amphibians and reptiles depends more on the environment to regulate temperature. Mammals and birds more depend on the seasonality of temperature. So we have two questions here. What is the impact of the S3N scenario across taxa related with the physiological difference? And what's the effect of the S3N scenario related with what happened with the protected areas, the biodiversity inside of the protected areas across the Americas? So we use the SESWAC model to generate the bioclimatic variable related with these mechanisms, water energy balance in seasonality. And we can project the change of species richness in the Americas. Blue colors means how many species can be gained, or the red colors means how many species can be lost in the future. You can see in this part amphibians, reptiles, mammals, and birds. You can see these more dark red colors in these two groups in comparison with mammals and birds. More affected this taxa in comparison with non-SRM scenario. So SRM tend to affect more disease groups across the geography, more in the temperate regions. But this pattern is more difficult to interpret in this way. So you can compare where is the regions where the project low species richness is greatest. So you can see this color represent the no SRM project more losses. You can find these colors in different taxa. It's very scattered across the geography, where the SRM scenario project more losses, tend to concentrate to the temperate areas, and similar projection on both scenarios. So it's not very easy to get a straight answer about this, the impacts. So in terms of the taxa across the geography, you have a non-stationary response. So for the next question, what are about protected areas? So we know that the protected areas are very important for the carbon storage. So we know the timely mitigation is very important to support the integrity and the network of the protected areas. So the question here is SRM can buy time to mitigation. So we have to want to test if SRM what is the effect on the biodiversity inside of the biodiversity inside of the protected areas. So we can find that species richness losses tend to amplify under SRM scenarios across the different categories. Is a kind of different management of the biodiversity or the lands across the different categories, across the different taxa, tend to be amplified, the species richness losses. So in terms of the comparison, birds and reptiles tend to lose more species than amphibians and mammals. So the message here is tend to be is biodiversity loss could be reduced across the areas. So can be the implication is could be affect the carbon storage in the system. So we can test more with other taxa, basically with diversity of trees to connect with the, especially with the carbon carbon storage. So some conclusion here is with this approach, we can adapt to compare impactors with different parameterization of GCM, so different time horizon or different taxa. So these hypotheses, water energy and seasonality, are very important to these taxa, amphibians and reptiles, because are related with across the physiological mechanisms. So the balance between temperature and precipitation is very important for these organisms. So you can isolate the variables. You can see the variables, how they related to this, the impact across the geography. So we can need to think more deeply about this, so include more other taxa, for example, trees, see to other Earth regeneration strategies have the same impact, testing different parameters to integrate more the other dimension of diversity, for example, traits, to include functional diversity, more related with the ecosystem functioning, for example, carbon cycle, to not focus only in the species numbers here. That's very important. We are working on completing, updating trait databases to run models, functional diversity for amphibians, but we are working on modeling functional diversity for birds. We are working on that. That is to run these projections on this other dimension of diversity. That's for now. Thanks for the guests for this funding. Thank you very much.
Thank you. We are moving for our last presenter. Shinu is from India and will present the impacts of SRM.
Good afternoon. My name is Shinu Wilson. I'm a Degrees Initiative funder researcher working with Professor Bala. So first of all, I would like to thank Degrees Initiative to give me an opportunity to present our work here, and Professor Bala to introducing me to this field. So today I am going to present on the work that we are doing on the topic impact of stratospheric sulfate aerosol geoengineering on Indian monsoon circulation and precipitation pattern. The outline of my presentation is a brief introduction, then objectives and the data we used, and the preliminary results, and summarizing it. Introduction. I'm not going to describe much more about the sulfate aerosol geoengineering, as you all know about it. It is proposed as the potential strategy to mitigate the impacts of climate change. And the global effects of the SIA on the temperature and the precipitation is extensively studied. If you go to the poster section, you might see work on the precipitation and temperature. So the gap is that the influence of the SIA on the regional climates, especially on the tropical circulation, is not well understood. So that we are looking. So the main question is whether SIA can counteract the climate change-induced changes in Indian summer monsoon circulation and precipitation. The main objectives are they to assess the potential impact of SIA on the Indian summer monsoon and to investigate the effect of SIA on monsoon circulation. For this study, we are analyzing the output from the GLANCE experiment. The main target of this experiment is to maintain the climate condition at 2020 under RCP 8.5. So for that, they are maintaining the global mean surface temperature and maintaining the interhemispheric surface air temperature gradient and maintaining the equator to pole surface temperature gradient. For that, there are three ensembles simulations are doing. For the first one is control ensemble. It's a 20-member ensemble based on the CMF5 RCP 8.5 scenario for 2010 to 2030. And next one is baseline scenario, that is RCP 8.5. The three control simulations are extended to 2097 to represent the future RCP 8.5 pathway. And other one is the SA ensemble. It's a 20-member ensemble for 2020 to 2097, designed to offset the warming under RCP 8.5 using the sulfate aerosol injection. For that, they are injecting the sulfate aerosols at 4 locations, 15 degree north, 15 degree south, 30 degree north, and 30 degree south at 5 kilometers above the tropopause. In this study, we are taking, for the present day, we are taking 20 years, that is 2011 to 2030. And for the future, we are taking 20 years from in the end of the century, that is 2071 to 2090. We are in this study, we are mainly focusing only on the Indian summer monsoon. So the season we took is June to September. And to find out the global warming effect, what we are doing is we are finding the difference between the RCP 8.5 and the control. And to find out the combined effect of the global warming and SAI, we are find out the difference between the glance and the control. Yeah. This is, we are presenting only the preliminary results, and this is for the surface temperature. In the top panel is for the global warming effect or the RCP 8.5 scenario, and the bottom panel is for the SAI scenario. From this, we can see overall there is a warming, and the land region is warming more than the ocean region due to the lower specific heat capacity. And over India, there is India warms about 3 degrees Celsius. In the oceanic region, we can see there is a warming over Western Indian Ocean than Eastern Indian Ocean. This implies a positive presence of the positive Indian Ocean dipole. And in the under SA scenario, what we are seeing is over the India, the domain average temperature change is, with respect to the control, is minus 0.04 degrees Celsius. That is almost offsetting, but there is a regional variation with residual warming over the north of India and residual overcooling in the in the southern parts of India. And for precipitation, over India, there is the rainfall is increasing approximately 14% under the, with respect to the control under the RCP 8.5 scenario, and there is a reduced rainfall in the East Indian Ocean and enhanced rainfall in the West Indian Ocean. This implies the positive Indian Ocean dipole pattern that we see in the previous slide also. Under the SAI scenario, the rainfall is decreased approximately 10% over India with respect to the control. That means SAI is under the SAI scenario, the increased precipitation under the RCP 8.5 is completely offset. It's not only completely offsetting, it is there is an additional reduction in the precipitation of about 10%. So we have to find out the reason why there is an additional reduction in the precipitation. We have to find out the answer to this question too. And this is for the wind at the lower troposphere and the upper troposphere. Those who don't know about the monsoon circulation, I'm just briefing it. In the southern Indian Ocean, there is a high called Mascarenes high during the summer season, and a heat low or this region in Indian region and the Pakistan region. So the wind flow from the high pressure region to the low pressure region. When the wind flows crosses the equator, it turns right due to the Coriolis effect and flows through India as a westerly called the low-level jet stream. And there is a cyclonic circulation over India. It's not clear here. And from here it rises, and in the upper troposphere there is an anticyclonic circulation, or there is a South Asian high with westerlies in the northern flank is the subtropical jet stream, and easterlies in the southern flank is the tropical easterly jet stream, and it sinks over the Mascareign high. This is the monsoon circulation. And under global warming, what we are seeing is there is an anticyclonic anomaly, anomalous anticyclonic circulation or Indian region with easterlies in the equator and westerlies in the over India. And this westerlies will enhance the low-level jet stream. And in the upper troposphere, what we are seeing is there is a anomalous cyclonic circulation. That means the South Asian high or the anticyclonic circulation is weakening. And there is westerly anomaly here. That means the tropically easterly jet stream is also weakening up. So in the upper troposphere, under the global warming, the circulation is weakening. And under the SA scenario, there is an easterly anomaly over the Indian region, means the low-level jet stream is weakening. And in the upper troposphere also, we can see a anomalous cyclonic circulation, which means the South Asian high is weakening. So the main message is that the projected changes on the monsoon circulation under global warming is not offsetting under SAI. There are numerous indices to represent the monsoon circulation, like Webster-Yang index, monsoon circulation index, monsoon hardly circulation index, like that. But here I am only presenting only one, that is Somali jet speed index, proposed by Bose and Emmanuel 2009. It is based on the magnitude of the wind. The maximum wind speed of the low-level jet stream is found near the Somali region. So we take this region, the magnitude of wind in this region. And from this time series, we can see the red line is the RCP 8.5, and the blue line is for the glens. From this, what we are seeing is the Somali jet speed index is weakening under RCP 8.5, and there is little to no weakening to the Somali jet speed index under SAI. Then next is Indian Ocean Walker circulation, that is the zonal circulation over the Indian Ocean. It is characterized with anomalous rising motion in the East Indian Ocean and descending motion over the West Indian Ocean. And Sharma et al. 2022 proposed the IWC index. It is based on the omega at 500 hectopascal, which is the difference between the West Indian Ocean and the East Indian Ocean. And under the global warming, the Indian Ocean Walker circulation is weakening. It is attributed to the presence of the positive Indian Ocean dipole under the global warming that we see in the previous slides. And under SAI scenario, the Walker circulation is slightly strengthening. And this is the vertical velocity at 500 hectopascal. The positive values means the descending motion, and the negative values means the ascending motion. Under the global warming, there is a descending motion over the East Indian Ocean and ascending motion over the West Indian Ocean. This also implies the presence of the positive Indian Ocean dipole under global warming. And under the SAI scenario, there is a large descending motion or sinking motion over Indian region, which leads to reduced convection, except in the peninsular region. And these are all the preliminary results. We need to do more analysis to answer the question that we posed here. So I'm just summarizing it. Under SAI, domain mean temperature remains fully offset over India, but shows inter-domain heterogeneity with the residual warming in the northern parts of India and overcooling in the southern parts of India. And the increase in precipitation under RCP 8.5 scenario is not only offset under the SAI scenario, but also leads to an additional reduction of 10% over India. And the increased, projected changes on the monsoon circulation under the global warming is not completely offset under SAI scenario. And further analysis is needed to understand the underlying mechanism driving the additional reduction in the precipitation under the SAI scenario. Thank you.
Thank you. Now I invite the four speakers to sit down here in front. And while you come, I will summarize their works here. Michael present for us the changes in the climate zones, and her first hypothesis was obtained in his work. Changes are in the climate zone, the changes are similar to SSP, more or less similar to the SSP 245. Liu talked about the heat waves on Southeast Asia, showing a decrease of the temperature of hot days in the future using SAI. And in general, the duration of the heat waves are from 5 to 10 days. Julián talked about the species and showed that SAI cause a negative, in his study, there is a negative impact in the species, amphibians, mammals, birds, and reptiles. And our last speaker, Shinu, talked about the impacts of SAI in the monsoon circulation, and one interesting result is about the Somalian jet speed that is restored under SAI. Now we have time for questions. John is the first one.
Yeah, thanks. That was really interesting. Julián, I haven't seen that kind of analysis before, and I wonder how robust it is if you have different realizations of the same model. Do you get a lot of noise in it, or do you think this is very reliable, these findings?
We have room from on the projections. We don't have a replicate of the in the future or the species richness, but the trend of the temperature and precipitation tend to be similar in the region. So I think the parents of in the future of the species richness change will be similar.
Can I just, I would ask Michael a similar question, in fact, that you only looked at one model there, Michael, and so it's a bit unfair to say, do you think it's robust between them? But I think these are very important things to know how model-dependent these kind of results are.
IPSL is similar, and depending on how much work Jay got done this week, I can email you with the other three. But no, my general sense is I think that these results are going to be relatively robust unless there are very, very large intermodal spreads in hydroclimate, which I have not seen on a global basis, although I would imagine for individual regions, which is something we want to look at, might be a more complicated story.
Questions?
Can I actually ask a follow-up question?
Yes, you can.
I'm going to actually ask a follow-up question to John, if that's okay. So you trained your machine learning model on present-day species distribution and then apply that to future changes. Are you concerned about the robustness of, so it's trained on present-day distribution where theoretically these things have evolved over a very long time period and have reached equilibrium versus we're very interested, right, in non-equilibrium changes where, I don't know, maybe the frogs would be happier if New York was more like Tallahassee in 500 years, but I'm not sure they're going to be happier mid-century. So is there some kind of, I guess, applying the machine learning present-day things to the future that gives you pause, or do you have some way of validating that?
Can you say the last part again?
Oh, sorry. So are you confident in applying the present day relationships to future changes, or do you have some way of validating that those work?
So I'm confident in the calibration part because we testing different with different partition of to avoid the overfitting the model. So we don't have a way to validate in the future. So that part is the problem with ecological models.
Sorry, I'm really interested in this topic. Can you validate it with the past based on the fossil record?
That is very interesting, but these models have no way to validate in the past if we don't have data for that part. Yeah. Another data are possible because you have that data, but this kind of model, no.
We have a question.
Right. I want to ask about the Indian precipitation changes. So you found that there would be a 10% precipitation decrease if we stabilize at 1.5 degrees Celsius with SAI under the high emission scenario compared to precipitation today. Am I getting that correct?
10% reduction with respect to the present day.
Okay, yeah. Right. But okay, and it's a pretty intense SAI scenario. You would do a lot of injection there. So maybe in reality, like in more realistic scenario, it would be a bit more manageable, perhaps. And also, can you speak on like water availability? Because how would evaporation? Okay, yeah.
Yeah, further analysis required, but we check the precipitable water and all. Under global warming, there is excess precipitable water, and in the SIO, there is a reduction in the precipitable water over India.
Okay, thank you. So my question also will go for Shinu about the precipitation over Indian monsoon. So I think in this study, can we advise the stakeholder with this result, or will we need to go further? Because we are talking about Indian monsoon, this is the local system, it's not global. So I think is maybe for me is, can you use regional climate modeling to see better what is going on? Because this result for now, I'm a little bit confused or afraid to say that we can convince people with this. This is my concern.
Do you want to help her?
Yeah, obviously, I'm sure we need to look at more. In fact, even before going to downscaled results, I mean, this is just a glance, only one model, right? So, but in general, I thought, we know when the global mean temperature is offset, the global mean precipitation actually decreases. This is a very well-known result, and particularly that will be even more severe for the tropics because most of them, the sulfur acts really pretty good in the, because that's where you have sunlight. So, but I think qualitatively the results, I don't think will change. But I think how much, I'm not sure whether it is 10% or 5%. I remember talking to her 5%. But anyway, I think, the quantitative, I think we have to really, I mean, that's the real purpose of starting this work. We really want to understand. In fact, we did also look at G6 sulfur and G6 solar as well. So these, I mean, the broader qualitative results are kind of, robust across the model, but we need to kind of get the handle on the numbers.
Thank you.
Just a related comment on that. I was very happy to see you did the Walker circulation things. I mean, I remember when we looked at it with G4, we found an interesting movement east from the over Africa, in fact, and the rainforest savanna boundary. And so if you're looking at just the change in that, but it might be very good to have a look at the geographical location change as well.
Okay, sure. Thank you.
On the heat stress work. So I know, I guess that was just dry bulb temperature, right? I guess the gist of my question is going to be, have you considered at all including humidity in that as well? I know humidity changes are really hard to get right in these types of models from my understanding, and I know lots of issues, but I'm curious if you've thought at all about how humidity might affect your results. Yeah.
Thanks for the questions. So at the moment, we are yet to consider the humidities because, it's not easy to get like humidity's historical result to bias correct the model. So like, for example, the historical data that we managed to get is from era 5. So it's not really like observation data. So but that one is the best for Southeast Asia. But for rainfall, yes. For rainfall, currently we are considering to use the rainfall, to study the drought risk by also incorporating the population information and so on. So not only considering the physical aspect, but also the social aspect, yeah.
I have two questions, and they're totally separate. One is for Leong, and then the other one is on Julian. So the first question is, I was checking at your heat wave, the counts of heat wave, and you mentioned that there was initial reduction in the beginning and then eventually increasing. But you measured, you showed it in counts. I was just wondering, compared to the past information that you calibrated, is this like lower or higher than the past heat wave counts?
Oh no, it's actually increased, but the increases is not like as serious.
How much higher?
Oh, I have to look back the.
No, because this area, recently we've been having a lot of heat waves, and we've been canceling classes. Yay for the students.
Yeah,
but
and even Malaysia, we canceled the class.
Yeah.
This one.
Oh.
Next one.
Which
HWN, the number.
Numbers. Okay, the last.
Just the last few. Yeah, this one. So it's blue one first, and then.
So like, okay, for example, in the next 10 to 20 years, so the number will increase maybe like 2 to 4 times, depending on the regions. Like maybe previously it's 3, so maybe in the future might be like 5 or 6. So the number is actually increased, but yeah, for sure, like when we go to the mid of the century, the increases will become more. Yeah, okay. Yeah, because of the increasing of the temperature. Okay.
Thank you. And another is on the species richness. I really liked your presentation, but I was wondering, so does this mean that with SAI, biodiversity would be negatively affected despite it, cooling the earth? So it showed a lot of like the fuchsia pink pictures had more than the yellows in your maps. Where is it? This one, yeah. So does this mean that ARISE SAI projects would lead to more losses in species richness for, all these selections of biodiversity? And does that mean SAI is bad, in your opinion?
It's hard to say what is more bad. So what is, because you can see the more richness for each group is in this region, the tropics. So they decrease to the poles. So you can see, no rise is more effect in the tropical region. So SREM is good to say species in the more biodiverse regions, but you have a no stationary response because it's very scattered. The response of the impacts very close, so we don't have we don't know exactly what happened. That maybe it's because the combination of the variables, the temperature, precipitation changes, have an effect, kind of the evapotranspiration effect across the distance. So it's very different. So we don't know exactly what is the most impact across this. So it's very difficult to get the balance.
Can I follow up? Just very quickly. So because this result, this compares the past species richness computation, so using past historical data versus future, right?
Yeah.
This is future.
Yeah.
So compared to the past, more losses in biodiversity is estimated by your model, right?
Yeah.
Okay.
Only geographically.
Geographically. Yeah.
Our last question, okay? Yeah.
Okay. Just joining the conversation on this. One, I would really encourage you to rerun this analysis with something like G6 sulfur, or I think that if you applied the same thing to mitigation, you would find that mitigation is bad because it decreases species richness, because your species richness is so sensitive on temperature. I think that this is, I really like this way of thinking about it, but the interpretation is very, very difficult, the way you're presenting it now.
Okay, Julián.
Thank you.
I know that this section is very interesting, the discussions are great, but we need to finish. We need to end our section.